Hi guys, welcome back to our discussion on infinite series. So in this video, we'll talk about absolute and conditional convergence. Okay, do you know that there are series that contains both positive and negative terms and not an alternating series? Like for instance, if you're given summation of sine n all over n squared, where n is from 1 to positive infinity, that if n is 1, you have sine 1 over 1. If n is 2, you have sine 2 over 2 squared or 4. If n is 3, then you have sine 3 all over 3 squared or 9, plus and so on and so forth. So the terms of this given series contains both positive and negative terms, but this is not an alternating series because some of the terms are positive and some of the other terms are negative, but not alternating. So one way to obtain some information about the convergence of this series is to investigate the convergence of the series summation of absolute value of sine n all over n squared, where n is from 1 to positive infinity. By direct comparison, in trigonometry, if you can recall, the absolute value of sine n is less than or equal to 1 for all n. Why? Because if you can recall, the value of sine n ranges from -1 to +1. So when you take the absolute value of sine n, this is less than or equal to 1 for all n. Then dividing both sides of this inequality equation by n squared, we get absolute value of sine n all over n squared is less than or equal to 1 over n squared for all n greater than or equal to 1. And as you can see, because this series is a p series with p is greater than 1, we can say that the p series with this n term is convergent. No? And because this is bigger than this series, we can say that from the definition of direct comparison, that if the bigger series converge, then so does the smaller series. So by direct comparison, the given series or this series is convergent. Okay, so the next theorem tells you that the original series also converge. Okay, so it says here if the series summation of absolute value of a sub n converge, then the series summation of a sub n also converge. The converse of theorem 9.16 is not true. Like for instance, the alternating harmonic series of this form, summation of -1 raised to n plus 1 all over n, where n is from 1 to positive infinity, which is equal to 1 minus 1 half plus 1/3 minus 1/4 plus and so on and so forth, converge by the alternating series test. But we know from the fact that the summation of 1 over n is a harmonic series, and so harmonic series is a diverging series. So this type of convergence is called conditional. So by definition, number one, the series summation of a sub n is absolutely convergent when the summation of absolute value of a sub n converge. And number two, the series summation of a sub n is conditionally convergent when the summation of a sub n converge, but the summation of the absolute value of a sub n diverge. And one example of number two is this alternating harmonic series. This is convergent by alternating series test, but when you take the absolute value of this, the series or the summation of the absolute value of the n term of the given series diverge. So we can say that this is conditionally convergent. So as an example, suppose we are asked to determine whether each of the series is convergent or divergent, and then classify any convergent series as absolutely or conditionally convergent. Okay, so our first example is the summation of -1 raised to n times n factorial all over 2 to the n, where n is from 0 to infinity. That if the value of n is 0, then you have 0 factorial over 2 to the 0 times negative 1 to the 0 is 1. So we have this as the first term. If n is 1, then we have negative 1 raised to 1 is negative, then 1 factorial all over 2 to the 1. If n is 2, then we have negative 1 to the second, so that's positive, times 2 factorial all over 2 to the second, and so on and so forth. So this is an alternating series because the sign of the terms alternates. So what we need to show is we need to check whether the terms of the series are decreasing terms. And then second is we need to show that the limits of the n term is equal to 0. Okay, for the first term, the value is 1 because 0 factorial is, that's 1, and 2 to the 0 is 1. So the first term is 1. Okay, next. The second term, this is 1 over 2 factorial. So that's positive 1 over 2 or 0.5. So 1 is greater than 0.5. How about the second? 2 over 2 squared. So that's 1/4 or also 0.5. So this is this is equal to 0.5. Okay. And then the last, this is 3 factorial is 6 all over 2 cube is 8. So that's 6 over 8 or 3 over 4 or 0.75. So meaning this is less than. So this is non-decreasing. So therefore, we can conclude by convergent, by alternating series test that this series is divergent. But we have to check using other tests whether this series is divergent. So we can use ratio tests. The reason why I use ratio test is because the n term contains n factorial and exponential term. Okay, so let us recall that by ratio test, we have to evaluate the limits of u sub n plus 1 all over u sub n, where u sub n plus 1 can be obtained by replacing all the n variable by n plus 1. So we have negative 1 raised to n plus 1 times n plus 1 factorial all over 2 to the n plus 1 times, instead of division, I use multiplication, but I need to get the reciprocal of u sub n, which is 1 over u sub n. So I have 2 to the n all over negative 1 raised to n times n factorial. Then I rewrite negative 1 raised to n plus 1 as product of negative 1 raised to n and negative 1, n plus 1 as n plus 1 times n factorial, and 2 to the n plus 1 as 2 to the n times 2. Then we cancel out common factor, negative 1 to the n, 2 to the n, and n factorial. So we have negative of n plus 1 all over 2. But by taking the absolute value, we get n plus 1 all over 2. And by replacing all the variable n by infinity, we have infinity plus 1 all over 2 is infinity, which indicates that, if you can recall, if the value of rho is greater than 1 or equal to positive infinity, then we can conclude that the series diverge. Okay, for the second example, given the summation of negative 1 raised to n all over square root of n, where n is from 1 to positive infinity. So if the value of n is 1, then we have negative 1 over square root of 1. If n is 2, you have 1 over square root of 2, and so on and so forth. And as you can observe, the first term of the alternating series is greater than the second term. The second term is greater than the third term, and so on and so forth. So this is a decreasing. This series is a series with decreasing terms. And then letter B, we have to show that the limits of the n term of this alternating series is equal to 0. So to evaluate, we replace all the n variable by infinity. So we have 1 over square root of infinity, but square root of infinity is infinity, and 1 over infinity is 0, which means that because the two conditions are satisfied, so we can therefore conclude that the series converge. Also, because the given alternating series is convergent using the alternating series test, we have to check whether the series is conditionally convergent. Okay, from the given series, if you take the absolute value of the nth term, so we get this series with positive terms, 1 over square root of 1 plus 1 over square root of 2, and so on and so forth. But this series can be written as summation of 1 over n raised to 1 half, where n is from 1 to infinity. And if you can recall, this series is a p-series with p is less than 1. Okay, and because this is less than 1, this series is divergent. And because this is divergent, and previously, by using the alternating series test, we have shown that the series is convergent. So therefore, we can conclude that the series is conditionally convergent. So in summary, we can say that if the series summation of a sub n converge, then the series summation of a sub n also converge. Also, by definition, the series summation of a sub n is absolutely convergent when summation of absolute value of a sub n converge. And second, the series summation of a sub n is conditionally convergent when summation of a sub n converge, but summation of a sub n or absolute value of a sub n rather diverge.